This afternoon we're going to work on this practice problem right here. We're going to solve for shear and bending moment diagrams analytically. So basically what we have here is a 12 kilonewton constant distributed load across section AB for 3 meters. These two supports are journal bearing, so they apply only vertical reactions. And then we have a distributed load that varies from 12 kilonewtons to 0 at the end. And here you can see the profile of the beam. 11.6, 11-68, it says the shaft is supported by smooth journal bearings, 1 and 2 at A and B. They only exert vertical reactions on the shaft, so there's no moment reaction here. Determine the smallest diameter D if the allowable bending stress is sigma allowed equals 180. So really what you need to do, if you step back for a second, is you need to figure out where the maximum bending stress is, and that will tell you where you're going to have the maximum normal stress. And from there, you can get the diameter D based on sigma equals MC over I. So first of all, we're going to need to solve this by looking at, draw my FBD here. So remember, we have a constant distributed load here, and then one that varies from 12 kilonewtons per meter to 0 here. So FR1, we need to figure out the resultant. Now remember, since it's a constant load, this distance here is going to be 1.5 meters. Let me just double check that. 1.5. So it's half of 3. And then this triangular load over here is going to act 1/3 from this journal bearing B, or 2/3 of 1.5, or 1 meter from the end. So let's draw that. So this here is going to be 1 meter from the end, 1 meter. So what is FR1? Well, FR1 equals your distributed load times the length, or the distance which it acts over. So it's 12 kilonewtons per meter times 3 meters. So your meters cross there, you're left with kilonewtons. That equals 36 kilonewtons. FR2, I always think of this as it goes from 12, it goes down to 0. So really your average distributed load is 12 plus 0 at the end divided by 2. And then you're going to want to multiply that by the length at which it acts over. So this is going to be equal to 12 over 2 is 6, so 6 kilonewtons per meter. This is an average times 1.5 meters. Equals 9 kilonewtons. Okay, so you go back to class. We talked about the first thing you really need to do is solve for your reaction. So that's RA and RB, and we know since these journal bearings only provide vertical force, that there's no moment at A or B. So in order to solve for RA and RB, if you take the moments about A, that eliminates A as a variable. You're left with one known, and one unknown, and then you can solve for RB. So sigma M about A equals 0. We do positive counterclockwise, and that's going to equal, so FR1 about A is doing a negative, it's rotating clockwise, so it's going to be so it's negative, so negative FR1 times 1.5 meters. 0.5 meters. And then you're going to have RB, which is acting in the positive direction, RB times 3 meters. And then FR2 is acting in the negative direction because it's doing this. So that's going to be so it's going to be 3 meters to here plus 0.5 meters. So this distance here is actually, little glitch there. Oops. This distance here is going to be 3.5 meters. Let's just go over that one more time. As always, my FPDs get a little cramped. So this is a triangle here, so we know the centroid of this distributed load as a triangle is going to be 1/3 of the way from here, so 1/3 of 1.5 is 0.5. So 3 plus 0.5 is 3.5, as I was saying. It's going to be minus FR2 bracket 3.5 meters. This all equals 0. Okay, so what's FR1? So it's 36. Negative 36 kilonewtons times 1.5 meters plus RB 3 meters minus 9 kilonewtons times 3.5 meters. Okay. So now we can solve for RB is equal to 28.5 kilonewtons. RB equals 28.5. I'll let you go through that exercise, okay? So now we use sigma Fy equals 0 equals RA RB minus 36 kilonewtons minus 9 kilonewtons equals 0. RA is the unknown, so RA we find if we sub and solve is equal to 16.5 kilonewtons. So here we have 16.5 kilonewtons, and here we have 28.5 kilonewtons. Okay, so now we can start to solve for forces analytically. And that's probably going to seem a bit daunting, but if you can get this down pat, your life, this stuff will become super easy, okay? I'm just going to scroll down here. And what we're going to do is we're just going to draw an FBD. We're going to do a method of section. I'm going to call it MOS1. And sorry for my bad small writing. Let me try that again. MOS1. So this tablet's hard to write on, sorry. So MOS1. And we're going to look this way, in this direction. Okay? So we're going to have our V going down. And remember this 4. Do I have it on the PowerPoint here? I think I do. Yeah, when you section this way and you look in this direction, can I draw? Yes, I can draw. You get V is positive down. If you're doing the other direction, V is positive up. Okay, we're going to assume, so that's V. We're going to assume an M this way. Okay, so what's happening with our distributed load? So this FR here, and if we just call this a function of X, this FR is really a function of X, right? Because the further you go, the more distributed load you take, right? So how do we describe FR as a function of X? Well, it's just distributed load times distance, right? So FR is going to equal 12 kilonewtons per meter times this distance X. And I'm just for simplicity's sake going to call it 12x. Okay? Where does FR act? Well, it acts in the middle. So it acts, and again, I have crammed so it's going to act at x over 2. Okay, so it's going to act at a distance of x over 2. So we need that for the moment. But for doing shear, let's just look at shear for a second. So we know we have 16.5 kilonewtons here. We have an FR coming down. We have some unknown V here. So we've got sigma Fy equals 0 equals negative V plus 16.5 minus 12x equals 0. So V is equal to is equal to 16.5 minus 12x. Well, let's just go back and remember this relationship here, that dV by dx equals W. And it's actually negative W because we just assume, we don't write the negative because the load's going downwards, we assume we're negative. So what's negative 12? What is negative 12? Well, there's the slope of negative 12 right there. Okay? and we've got this constant reaction of 16.5 at the end. So up until the next reaction B, this is your shear force as a function of x. So we could actually right now just draw that section of the curve, but let's just move on. We're running out of space here, so we're going to go to sigma m, so that's this m right here, equals 0, equals, well, if you think about it, we've got our m plus, that's our internal moment. We've got negative 16.5 x, right? And then we've got plus fr times x over 2. And this all equals 0. So m is equal to 16.5 x minus 12x times x over 2 squared, so it's negative 6x squared equals 0. So this function here describes the moment, and just a little hint here going forward, this is the dm by dx. Remember dm by dx equals v, dm by dx equals v. So then m is equal to the integral of your function v. So if you know how to take an integral, you'll realize that if you dm by dx equals v, you get m 16.5x, the derivative is 16.5, the derivative of negative 6x squared is 12x. So once you know this function, you can get this function. Now it gets a little more complicated when you have boundary conditions or applied moments, but essentially this is how it gets. Once you get the v, you just integrate to get your m. Or you do it analytically by taking the moments. But that's actually a pretty eloquent solution if you think about it. So let me just turn off my layers here. We'll go back up here to my second layer. So remember, v is equal to 16.5 minus 12x, and m is equal to 16.5x minus 6x squared. Okay? So how are we going to plot our v here? Well, we know when x equals 0, it's equal to 16.5. Remember, that's our reaction. So now we know it's going to have a slope of minus 12, and that's going to happen until it hits the next support. So that's going to happen at 3 meters. So 16.5 minus 12 times 3 is 16.5 minus 36. So we know that this value here is negative 19.5. Okay? So now let's look at our m here. We have 16.5x, and by the way, we also have this point right here, which is where the maximum is going to occur. Well, how do we solve for where this happens? Well, we set v equal to 0, so 16.5 subtract 12x equals 0. So x equals, drawing a bit of a blank on that right now, but it's going to be equal to 12 divided by 16.5. 12 divided by 16.5. No, it's going to be 16 divided by 12.5. That's not it. Have I copied it down incorrectly? 1 second. So v equals to 16.5 minus 12x. 16.5 minus 12x. Minus 12x. So yeah, it's going to be 16.5 divided by 12. 16.5 divided by 12. 1.375. That's right. This is going to be 1.375. So x equals 1.375. So this coincidentally is going to be where we get a maximum on our dm by dx. And we're going to want that value for our analysis, right? So recall this value right here. Nice and easy way to solve. So what happens to m at 0 if we want to plot m? Well, we know m is equal to 0 at that point, right? But what about m? 1.375. Well, you just sub. That equals 11.34. So we know this value right here, and of course I'm cramming stuff in here. Let me just erase that. Let's move it down a bit. Move it down here. That's going to be equal to 11.34. So when we know we have a positive slope here of 16.5, we know it's going to be 0. And then it's going to go down to negative 4.5. And how do we know 4.5? So n equals negative 4.5. And if you don't believe me, sub m equals m at 3 into this, and you'll get negative 4.5. So now we've defined the first part of our curve. And now I want to go into the next process of defining this part of the curve over here. So now we're going to work on this part right here. Okay, so how are we going to do that? Well, this is actually the trickiest part. So let's start that. So now we're going to look at the beam. Here's our FBD. Okay, we're going to draw our beam. This is going to be where our slice is. This is going to be the end of the beam. So our distributed load is doing this. Okay, we're going to have an FR. I believe we called this FR. FR2. And then we're going to have a reaction here, internal reaction here. We're going to have an internal moment here. And we've got this FR. So actually, right now, it's looking like a pretty straightforward curve. But let's see, because this actually can get a little complicated. So what you really need to figure out is your distributed load is a function of x. So what is that? So w is a function of x. The way we did it in class was, let's just look at this right. W is a function of x, and x, this is x here. And we're just going to say we're going in this direction. So we know we go from 0 to 12. And we know, so we're going to write 12 here. We're going to divide that by the distance that this distributed load, that it goes from 0 to 12.5, which is 1.5. And then we're just going to put x here. So think about this. Is x, if this is x equals 0, and I multiply it by 12 over 1.5, which by the way equals 8x, then I get 0, which is true here. At the other end, if I sub 1.5, I get the 12 kilonewton per meter distributed load, which is right here. So this is a good way to describe, this tells us our W of x. So any point of x along that distributed load beam, that's going to be our W. But W times L gives us the FR. So FR2, in this case, is going to be 1/2, because the distributed load is a triangle, it's going to be 1/2 8x times x. So that's going to be 4x squared. Okay, so that is FR2 as a function of x. So now, if I look at V, sigma Fy equals 0, I've got equals V minus 4x squared. So V is equal to 4x squared. So this value, this function here describes the value of shear along this section of the beam. Okay, so now what do we do with our moment? I just want to go back and do before we look at the moment, we're going to do one last sanity check. When I sub 1.5 into here, I should get, don't forget, the FR2, where is it here? FR2 is equal to 9 kilonewtons, right here. Yeah. FR2 is equal to 9 kilonewtons. Well, wouldn't you know, when I sub 1.5 into here, 1.5 is 2.25 times 4 equals 9. So this is how we know this FR2 is correct. It's one way to check, okay? So now we have the value of V, the function of V. Then we're gonna do our sigma m equals 0. And that's this m here. So we're gonna have m minus, remember this is positive, m minus FR2 times some distance, right? Well, it's x over 3 because the triangle is going up this way, right? So it's going to be, your centroid is going to be at the x over 3. This is going to be x over 3. And this all equals 0. Well, then m is equal to what is FR2? 4x squared. 4x squared times x over 3, which equals 4 over 3 x cubed. So now we have an m and a v. And one more time, look at v and look at x. If I differentiate m, I get 4 over 3x squared. Differentiated, I get 4x squared. So dv, again, we've just validated when we do it by analysis. Once we know this curve here, we can get this curve. So remember, it's dm by dx, let me scroll down, equals v. Right? So when we differentiate m, we get v. So once you know v, right here, you can get, you don't even have to do anything else. Okay, so this is once you know this complicated method, it's really the way to go to solve this problem. So let's look at, we've got 4x squared for our shear, okay? We want to go back up to our shear. So when we sub in 1.5 here, what do we get? So let's just say v at 1.5 equals 4 bracket 1.5 squared, and that equals 9. So we know that this curve here, starting here, is parabolic, and it goes up to 9. And then, well, we can see it's going to drop back down like that. And what was the reaction B? Sorry, let's just go back for a second. What was RB? RA equals 16.5. RB equals 28.5. Okay. And a 28.5 to 9. Well, what's 9 to 19.5? It's 28.5. So that shows you the reaction is being properly accounted for here. Now the last thing we have to do is this 4 over 3x cubed. Right? So what is that going to look like at 1.5? Something tells me I've done something wrong here. This should actually be negative. So if we're taking our m about here, we got positive m minus FR2x over 3. Sorry, I've done something wrong. I think this should be negative. Give me 1 second here. See what I've done wrong. So this m here is positive on the shear and bending moment, but it's negative here. So that means m is equal to negative 4x squared, which is negative 4 over 3. And let me just write this a little neater here. So negative 4 over 3x cubed. Well, remember this is negative 4.5. So if I take 1.5 and I cube it, and I times it by 4 over 3, so here we go. 1.5 x cubed times 4 divided by 3 equals negative 4.5. Not 4.5, so let me lift that here. So it's negative 4.5. And we know it's cubic, right? So it's going to do this. So that's how you solve a problem like this analytically. And once you can get this down, if you really sit back and think about it, you just need to come up with your shear curve. And I can take you through in class how to integrate. Remember, when you integrate, you have to have a constant, just in case you have boundary conditions that are non-zero. In this case, when we integrate this, yeah, let me come back to that, because we're getting negative here, and I need to come up with a way to explain that. But you can see the relation for now. I'll close the loop on that next week. But anyway, that's the solution to this problem.